Okay, so let's take a look at an example. It says solve differential equation using variation of parameters, so theorem 12. So our differential equation is y double prime minus 2y prime plus y equal to e to the x over 1 plus x squared. Okay, so the first thing we need to do is solve the homogeneous differential equation, so set it equal to 0 on this side. So let's do that first. Okay, so we're going to solve this guy first. Since it has constant coefficients in front of the y double prime, and y, we know one of the solutions looks like y1 say equals e to the mx. Okay, so when the solutions of this guy looks like e to the mx, so derivative then would be y1 prime would be m e to the mx, and y1 double prime would be m squared e to the mx. Let's plug into differential equation and find conditions on m that make it 0. So doing that, we get. Okay, so plugging into differential equation, place a y, putting y1. So we'll have then this y1 double prime is m squared e to the mx. Then it'll be minus 2 y1 prime, so it'll be minus 2 m e to the mx, then plus y1 e to the mx. Okay, then we're going to factor the e to the mx out on the left hand side. So doing that, we get then. So factoring the e to the mx out, we get this. And then this has to be 0. The e isn't 0 because e to any power is never 0. So therefore, this quadratic has to be 0. So note the e to the mx isn't 0. So that means that this quadratic has to be 0. And you could use a quadratic formula on this to solve it, or you could recognize that it factors, and it factors as m minus 1 squared. So let's note that here. Okay, so we note that this factors as m minus 1 squared, so our solution would be m minus 1 equals 0, so m is 1. So we're going to be using theorem 8 then to find the second solution. So we know one solution would be y1 equal to e to the x, and the y2 solution using theorem 2 would be x e to the x. So let's note that. Okay, so by theorem 8 then y1 equal e to the x, y2 equal x e to the x are two solutions of this differential equation equal to 0. Now we want to find the general solution of this star differential equation up here, and we're going to be using variation of parameters, or theorem 12. So let me write down theorem 12 here. Okay, so by theorem 12 then, the general solution of this differential equation up here is going to be c1 y1 plus c2 y2 plus u1 y1 plus u2 y2, where u2 is the integral of y1f over w dx, and u1 is integral of negative y2f over w, where w here is a Wronskian. Okay, so let's start computing these things. So I'm out of space here, so let me erase a few things and we'll keep going. Okay, so summarizing, here's our differential equation we're trying to solve, and here's the y1 and y2, which were the solutions of the homogeneous one, so when it was 0 on the side. So and here's how formulas for finding u2 and u1. We also have to find the Wronskian w. So my y1 is e to the x, so derivative of e to the x is itself. My y2 is x e to the x. So derivative, you'd have to use a product rule, so derivative of first function is 1 times e plus first function x times derivative of e to the x, which is itself. So it'd be this. Then you can factor the e to the x out. You'd have x plus 1 times e to the x. Okay, so let me put those values here and compute the Wronskian. So doing that, we get then. Okay, so plugging in Wronskian then, so it'd be y1, which is e to the x, times y2 prime, which is x plus 1 e to the x, minus y2, which is x e to the x, times y1 prime, which is e to the x. Now, the two terms have two e to the x's. So when you multiply the e to the x's, it becomes e to the 2x. So I'm going to factor it out of both of those, which I've done here. Then it'll be an x plus 1 left here, minus an x here. So the whole thing will just reduce to e to the 2x. Okay, so now we can start computing our u2 and u1. So we'll use our y1 e to the x here. Our f will be e to the x over 1 plus x squared. And our w is this guy. So plugging into this, we get then. So plugging in, so we have our y1 is e to the x here. Then our f is this guy, which I have here, divided by our Wronskian. Wronskian's this, so therefore when you divide it by, you can make it a negative exponent, which I've done here. Then you have e to the x times e to the x, which would be e to 2x, times e to the minus 2x, would be e to the 0, so it'd be just 1. So it looks like it's going to reduce to integral of 1 over 1 plus x squared. Okay, so it's going to be integral of 1 over x squared plus 1. And then you've recalled from Calculus 2 or Math 160, the integral of this guy is arctangent. So let me write it here. So it'd be arctangent. I guess it'd be arctangent plus c, but since we're just finding u2, you can just choose the constant always to be 0. So it's just going to be arctangent. Okay, now let's find our u1. That's going to be minus y2. y2 is x e to the x times my f, which is this guy, divided by Wronskian. So, which is this guy. So let's plugging these in, then we get then. So plugging in. So again, our y2 is x e to the x will be minus x e to the x times my f e to the x over 1 plus x squared from up here. And then divided by my Wronskian. The Wronskian's e to the 2x, when you divide, it'll become a negative exponent, which should be e here, which I've done here. And then multiplying the e to the x with e to the x is e to the 2x, and then you're multiplying with e to the minus 2x with e to the 0, which is 1. So it's going to simplify to be then integral of negative x over 1 plus x squared. Let me write it here. So we have this, I pull the minus sign out. In this one, we can actually use a u substitution. I'm going to let u equal x squared plus 1. So let's do that. Okay, so letting u equal x squared plus 1, then du dx would be 2x. Then multiplying both sides by dx, du would be 2x times dx. And then solving for dx, dividing by 2x here, dx would be du over 2x. So let's plug in to our integral up here then. Actually, you're going to write over here. So plugging in, we get then. So plugging in over here, so you'll have your x over u, because x squared plus 1 is my u, times my dx. But dx now is du over 2x, which I've put here. And minus sign in front still. The x's cancel here. Then I can take out the 1/2 in front, so it'll be negative 1/2, integral of 1 over u du. And the integral of 1 over u would be ln. So let me write that. Okay, so it's going to be then negative 1/2 ln of u. U is equal to x squared plus 1, so it's going to be negative 1/2 ln of x squared plus 1. So we found our u1 and we found our u2. Now we have our y1 and y2. So now we're ready to write the general solution using Theorem 12. So let's do that. But I'm out of space here, so I'm going to erase a few things and we'll continue. Okay, so summarizing, we have our y1 is e to the x, our y2 is x e to the x, our u1 is negative 1/2 ln of x squared plus 1, and our u2 is arctangent. So by Theorem 12 then, the general solution is going to be c1 y1 plus c2 y2 plus u1 y1 plus u2 y2. Okay, so it'll be c1 y1, y1's e to the x, plus c2 y2, which is x e to the x, plus u1 y1. My u1 is this guy, the negative 1/2 ln, and my y1 is e to the x. I'm putting the e to the x in front of the ln just so it looks nicer. So it'll be negative 1/2 e to the x ln of x squared plus 1, then plus u2 y2. So my u2 is arctangent and my y2 is x e to the x. Again, I'm putting the e in front of the arctangent just because it looks nicer. Okay, so this would be the general solution to our differential equation up here. So we're done. So let's leave it there.